Hi there. Today we are investigating the concept of constant velocity. To do so, we will do this with the help of Newton's second law, force is equal to mass times acceleration. If constant velocity exists in a system, then the net force on the system will be equal to zero. In an attempt to observe constant velocity right here in my own home, I took a basketball and rolled it across my coffee table from good old IKEA. My friend videotaped it, and then we uploaded it to Tracker to analyze our example. Here's my example. There was a couple things I needed to do in Tracker to properly analyze my life example of constant velocity. My realistic example is better to say. First, I set the calibration stick, which is right here, to 0.25 meters, which is the average diameter for a basketball, and then I took the origin of the axes, which are right here, and attempted to place them at about the origin or the center of mass in the basketball. I also made sure that the axes were basic as I always assume them, which is that positive x is in the right direction, which is over here, and that positive y is in the upward direction. Overall, I observe about 0.708 seconds of the ball's velocity, and that is between these two black arrows, and I made sure to record and analyze the section after my hands leave the ball and before that the ball goes off the table. As you can see over here in the graph, the ball's velocity is almost constant, and here it's a position versus time graph. There's a few fluctuations in between which have to do with my placement of where I put the origin of these little diamonds as the ball rolls along the negative x-axis. To compare the real-life example to a computational model, I use the basketball's mass, initial velocity, initial position, and final observed time in my VPython code. With this, I was able to predict the object's future motion velocity. There was a few parts of the VPython code that I want to explain really quick. This line, ball.position equal to vector plus 0.012, 0, 0, and ball.vel equal to vector negative 1.05, and 0 are both really important. These are for the initial conditions, and I plug these numbers in based off the Tracker graph. T is equal to 0 because in the Tracker video, I'm assuming that the ball is leaving my hands at initial t is equal to 0. That's the initial time that it's leaving. For the second major part of the coding for VPython, I have fnet is equal to 0, 0, 0, because constant velocity can only exist in a system where the total force and acceleration is equal to 0. This is our main assumption with the computational model. We have to assume fnet is equal to 0 in order to obtain some kind of constant velocity. The velocity equation is the next line of code defined, which is right here. Ball.vel is equal to ball.vel plus fnet divided by ball.m, which is the mass of the ball, plus delta t, which is 0.708. And then over here, the next line, the next really important, is the position equation, which is ball.position is equal to ball.position plus ball.velocity plus delta t. And this line right here, advance the clock, t equals t plus delta t. This is to advance time as the code runs, so each time it's like a loop. Every time this happens, the ball will move forward in its velocity and its position.